Hello fellow problem solvers, so today we're going to be doing a number theory problem, namely let a and b be positive integers such that, or natural numbers, such that a plus 1 over b plus b plus 1 over a is a natural number, and we need to prove that the GCD of a and b squared is less than or equal to a plus b. I invite you to try this problem out for a minimum of 5 minutes, ideally 20 minutes, but not more than an hour. If on the other hand you'd like to go along with us, I suggest you give it a go for the next 5 minutes. Put your first ideas out on paper, and with that, let's begin. So the first step in this sort of problem, there's two things to think. You can go at it forwards or backwards. Forwards, okay, what do we have? We have this as an integer. Well, this just means that AB, what is this like? This is AB over A squared plus B squared plus A plus B. So your A squared plus B squared plus A plus B over AB is an integer. So this just means that AB divides this, like this is the problem statement. AB divides A squared plus B squared plus A plus B. And with this now, let's look at what we have to prove here. The GCD of A and B. Well, it makes sense to then just say like A is equal to dx and B is equal to d times y. This is d times x, d times y, where d is the GCD of A and B. And now what we have to prove is that d squared is less than or equal to, actually, is less than or equal to dx plus dy, i.e. that d is less than or equal to d plus, like x plus y. So this is what we have to prove now. This is going at it backwards. And now let's go forwards again. What do we have as the problem condition? Well, once we get rid of, we first get d squared xy divides d squared x squared plus d squared y squared plus dx plus dy. We can get rid of the d and we have dxy divides dx squared plus dy squared plus x plus y. And we need to prove that x plus y is greater than or equal to d. How do we do this? From here. And here's where I invite you to pause for another 5 minutes, even 10, maybe 15 minutes, and try to figure this out. And here is the next step. Here's the next, so this is the next step. D divides this, which divides this, which divides this. Why do we look at it this way? Well, mind you, we have a divisibility relationship here. We want to get to x plus y being greater than or equal to something, like greater than or equal to d. And so we want to say isolate d on this side. And because when we have a divisibility relationship, a divides b, that means b is greater than or equal to a. So we want to see if we can have that here. And the reason we get d dividing all of these things is because now d divides this, which divides this. So d divides this. Now d divides dx squared. D divides dy squared. So d divides x plus y. And because d divides x plus y, and these are, mind you, in the natural numbers, that means that d is less than or equal to x plus y. The GCD is always, I think it's always positive. But in this case, it's definitely positive, and it wouldn't change anything if it was negative. So this proves this, finishes up our problem. It's a nice little, problem in number theory, sort of letting you see like how you do things with the GCD. And this is how. You try to, when you put the GCD is like write A and B in terms of their GCD, then you can sometimes get rid of some stuff. Sometimes there's a lot more useful things that you can do because now x and y are relatively prime, and then you can gain some new insight and information because of that. But here specifically, there wasn't that much of that. There was just d divides. Like I think the GCD squared divides a squared plus b squared. From here, that follows, because the GCD squared divides ab, and so also divides these two, and then the GCD squared divides a plus b. That's another way we could have ended the problem sooner, but I think this way is more systematic. This solves our problem, and as always, thanks for problem solving.